At the very edge of the Sun's dominance, a small, silent world continues its endless orbit. Mercury does not welcome visitors. It is a planet of extremes, where the Sun rises larger than anywhere else in the solar system, and where day and night are separated by temperatures that defy survival. For centuries, it was only a moving point of light in the sky. A world too close, too fast, and too dangerous to understand. But today, through measurement and observation, humanity has begun to uncover its story. A story written in impact scars, magnetic fields, and shadows that never see the Sun. This is Mercury. Mercury orbits closer to the Sun than any other planet in our solar system. At an average distance of just 58 million kilometers, it experiences solar radiation more than 6 times stronger than Earth. From Mercury's surface, the Sun does not appear gentle or distant. It dominates the sky. Yet Mercury is not simply a scorched rock. It is a world of extremes. A single day on Mercury, from sunrise to sunrise, lasts 176 Earth days. Its year, however, lasts only 88 Earth days. This unusual relationship between rotation and orbit creates a resonance. Mercury rotates 3 times for every 2 revolutions around the Sun. The result is a complex dance of light and shadow. Sunrise on Mercury is not simple. The Sun can appear to rise, stop, reverse direction, and then continue again due to orbital mechanics. The physics of Mercury's motion reveals the influence of gravity at its most precise level. In fact, Mercury's orbit was critical in confirming Einstein's theory of general relativity. Its perihelion, the closest point to the Sun, shifts slightly over time. Newtonian physics could not fully explain this precession. General relativity could. Mercury became a test of space-time curvature long before spacecraft ever visited it. Mercury has almost no atmosphere. Without a substantial atmosphere, there is no mechanism to distribute heat. During the day, surface temperatures can exceed 430 degrees Celsius. At night, they drop below -180 degrees Celsius. This makes Mercury one of the most temperature-extreme worlds in the solar system. The absence of atmosphere also means no weather, no wind erosion, no cloud cover. Impact craters remain preserved for billions of years. The surface resembles the Moon, heavily cratered and ancient. But Mercury is not identical to the Moon. Its surface contains vast plains formed by volcanic activity. These smooth regions suggest that Mercury was once geologically active. Despite its small size, its interior remained hot enough to drive volcanism. This indicates a complex thermal history. Mercury is not merely a dead remnant. It is a world that once reshaped itself. Mercury is unusually dense. For its size, it contains a disproportionately large iron core. Approximately 85% of the planet's radius is dominated by metallic core material. This makes Mercury the most metal-rich planet in the solar system. One hypothesis suggests that early in solar system history, Mercury experienced a massive impact that stripped away much of its outer crust. Another suggests intense solar radiation during formation removed lighter materials. Regardless of origin, the large core has consequences. Unlike the Moon, Mercury still possesses a global magnetic field. Though weaker than Earth's, it is significant. This magnetic field implies that Mercury's core remains at least partially molten. For a small planet so close to the Sun, maintaining a molten interior challenges previous models of planetary cooling. Mercury continues to surprise. Perhaps the most unexpected discovery about Mercury concerns water. Despite extreme daytime heat, radar observations revealed bright deposits at Mercury's poles. Later, the spacecraft Messenger confirmed the presence of water ice in permanently shadowed craters. Because Mercury's axis tilt is extremely small, some crater floors near the poles never receive sunlight. These regions remain in permanent darkness. Temperatures there stay low enough to trap ice. This ice likely arrived via cometary impacts. Even on the closest planet to the Sun, water can survive, if shielded from light. This discovery reshaped understanding of volatile distribution in the inner solar system. Mercury is not uniformly dry. It contains frozen records of solar system history locked in shadow. Reaching Mercury is more difficult than reaching Pluto. This seems counterintuitive. Mercury is closer to Earth than any outer planet. But proximity to the Sun creates a problem: velocity. Objects orbiting close to the Sun move extremely fast. To enter Mercury's orbit, a spacecraft must shed enormous amounts of speed relative to the Sun. It must effectively fall inward while continuously braking. This requires gravity assist. The spacecraft Messenger, launched in 2004, used a complex trajectory. It performed 1 Earth flyby, 2 Venus flybys, 3 Mercury flybys. Each pass adjusted its speed and direction. After nearly 7 years of travel, Messenger finally entered orbit around Mercury in 2011. It became the first spacecraft to orbit the innermost planet. The engineering required was substantial. Mercury's environment exposes spacecraft to intense solar radiation and heat. Messenger carried a ceramic sunshade to protect its instruments. Its orbit was carefully designed to minimize overheating. Exploration of Mercury required precision navigation and thermal endurance. Before Messenger, much of Mercury's surface was unknown. The earlier Mariner 10 mission in the 1970s had imaged less than half of the planet. Messenger completed global mapping. High-resolution imagery revealed a heavily cratered world shaped by impacts and volcanism. One of the most striking features is the Caloris Basin, a massive impact structure approximately 1,550 kilometers wide. This basin formed billions of years ago during a period of intense bombardment. The impact was so powerful that it produced weird terrain on the opposite side of the planet, fractured landscapes likely caused by converging seismic waves. Messenger also identified extensive volcanic plains. These smooth regions confirmed that Mercury experienced significant volcanic resurfacing in its past. This contradicted earlier assumptions that Mercury was geologically inactive early in its history. Instead, Mercury underwent complex internal evolution. It cooled slowly enough to sustain volcanic processes for extended periods. Mercury's surface is a record of early solar system violence. Messenger carried instruments capable of analyzing elemental composition. The findings were unexpected. Mercury's surface contains higher than expected levels of volatile elements, including sulfur and potassium. These elements are typically associated with cooler formation environments. Their presence suggests Mercury did not form under extreme high-temperature conditions as once believed. This challenged previous models of inner solar system formation. The data indicated a more complex early environment. Mercury may have retained volatile materials despite its proximity to the Sun. In addition, measurements confirmed that Mercury's core remains partially molten. This explains its global magnetic field. The planet is small yet internally dynamic. Geophysical data revealed contraction features, long cliffs known as lobate scarps. These scarps formed as Mercury cooled and shrank over billions of years. The planet is still evolving, slowly contracting as its core loses heat. Mercury is not static. It continues to change. Messenger ended its mission in 2015 with a controlled impact onto Mercury's surface. But exploration continues. BepiColombo, launched in 2018, is currently en route to Mercury. It is a joint mission between ESA and JAXA. BepiColombo consists of 2 orbiters: the Mercury Planetary Orbiter, the Mercury Magnetospheric Orbiter. Together, they will study Mercury's interior, surface, and magnetic environment with unprecedented precision. The mission aims to answer unresolved questions. Why is Mercury's core so large? How does its magnetosphere interact with solar wind? What is the detailed structure of its polar ice deposits? BepiColombo is performing a series of gravity assists similar to Messenger's trajectory. Arrival in Mercury orbit is planned for the coming years. Mercury remains a frontier. Despite its proximity, it is one of the least explored terrestrial planets. Humanity's first visit revealed complexity. The second may redefine our understanding of planetary formation. Mercury exists inside a region of intense solar influence. The Sun continuously emits charged particles known as the solar wind. At Mercury's orbit, this stream is far denser and faster than at Earth. Without protection, the solar wind can strip away atmospheres and erode planetary surfaces. Unlike Earth, Mercury lacks a thick atmosphere. But it is not entirely defenseless. Despite its small size, Mercury possesses a global magnetic field. This magnetic field creates a miniature magnetosphere. It is far weaker than Earth's, yet strong enough to deflect part of the solar wind. However, because Mercury orbits so close to the Sun, its magnetosphere is compressed. On the Sun-facing side, the magnetosphere is pushed close to the surface. On the opposite side, it stretches into a long magnetic tail. This constant compression and stretching create dynamic space weather conditions. Mercury's magnetosphere reconnects frequently with solar magnetic fields. These reconnection events funnel charged particles toward the surface. Unlike Earth, Mercury does not have a thick atmosphere to absorb these particles. Instead, solar particles directly impact the surface, releasing atoms into space. Mercury's surface is constantly bombarded by solar wind and micrometeoroids. These impacts eject atoms from the crust into a thin envelope around the planet. Mercury does not have a traditional atmosphere. Instead, it has an exosphere, an extremely thin collection of atoms. This exosphere contains sodium, potassium, oxygen, and trace elements. These atoms are continually lost and replenished. Solar radiation pressure can even push sodium atoms into comet-like tails trailing the planet. Mercury glows faintly in certain wavelengths because of this sodium exosphere. It is a planet interacting directly with its star. Every orbit, it is sandblasted by energetic particles. Over billions of years, this process has altered its surface chemistry. Studying Mercury's exosphere reveals how planetary surfaces evolve under extreme stellar radiation. This is not merely about Mercury. It is about understanding rocky planets orbiting close to other stars. At Mercury's poles, a different environment exists. Because Mercury's axial tilt is extremely small, some crater floors never receive sunlight. These permanently shadowed regions remain cold enough to preserve water ice. Radar observations first hinted at reflective material. Later confirmation came from MESSENGER. The presence of water ice on the closest planet to the Sun appears contradictory, but physics explains it. In permanent shadow, temperatures remain below freezing. Cometary impacts likely delivered water. Over time, ice accumulated and remained trapped. These polar deposits are geologically stable. Future missions, including BepiColombo, aim to study them in greater detail. Mercury demonstrates that even in extreme proximity to a star, volatile compounds can survive under the right conditions. This insight extends beyond our solar system. Many exoplanets orbit close to their stars. Understanding Mercury helps model their potential surface chemistry. Mercury is often overlooked. It lacks rings. It lacks a thick atmosphere. It lacks dramatic cloud systems. But it provides essential data. It tests gravitational theory. It challenges planetary formation models. It reveals how magnetic fields survive in small bodies. It shows how solar wind shapes exposed surfaces. It demonstrates how water can persist in extreme conditions. Mercury is not merely the closest planet to the Sun. It is a laboratory. Its environment approximates conditions faced by many rocky exoplanets orbiting red dwarf stars. Studying Mercury informs our understanding of planetary survivability. It teaches us about magnetic shielding, about atmospheric loss, about surface evolution under stellar radiation. Humanity measures Mercury not because it is dramatic, but because it is fundamental. In its silence and extremes, Mercury reveals the physics of proximity to a star. It is the innermost frontier,